everyone, today I'm going to do an example question, actually two example questions on mechanism. Okay, so as we talk about in class, okay, so you will have an overall reaction such as this question. Okay, so this is overall reaction. Okay, so this is before we started talk about mechanism. That's what we always have been talking about overall reaction. Okay, so overall reaction means we didn't really mention about the detailed steps. Okay, so we didn't talk about how it's from the reactants go to the product step by step. Okay, but then with mechanism, and then we proposed this could be the step actually happened. Okay, and then those are called elementary steps. Okay, so therefore for this particular reaction, okay, so there are two elementary steps. Okay, and then for writing the rate law for this overall reaction, we could, based on the mechanism, try to come up with the overall rate law. Okay, and then as we know, the rate law essentially, we have to do experiments to really determine what's the observed rate law. Okay, so therefore let's work with the mechanism and try to match the observed rate law. Okay, so now let's see. Okay, so for this mechanism, okay, so the first step is a slow step. Okay, as we know, the slow step means what? The rate determining step. Okay, so that means that's what really determines the rate even for the overall rate law. Okay, and because that's the bottleneck, right? That's the traffic on your home. That's the accident on the way home. That's what determines how long you'll be able to get home. Okay, so anyway, so over here, then we know, okay, so if the first step is the slow step, we should be happy about this. Okay, so we should be very happy. Okay, so therefore we can just start to write down the rate law for this elementary step, which should also be the rate law for the overall reaction. Okay, so now let's do that. Okay, so the rate, I'll just write over here, the rate for this slow step will be K, okay, rate constant times the concentration of the reactants to its power, and over here that have 1 mole to 1 mole ratio, so that'll be 1, right? Okay, and NO2 1. Okay, then you recognize, okay, so we have NO2 twice, so then we can reorganize this expression into K NO2 squared. Okay, so that's it. Okay, and then that's actually if people did experiments and then the observed the rate law for this overall reaction actually is also what we have been proposed. Okay, so then this matches. Okay, so that's good. Okay, so that means what we propose as the mechanism, as the elementary steps, were actually correct. Okay, so that's the end for this question. So that's super easy. Again, when you see slow step is the first step, you should be very happy. And one step, you're done. Okay, then of course there is the other situation. Okay, so now let's read this question. Okay, so again, ask you to write down the rate law for this overall reaction. Okay, so that's the overall reaction. And then with the proposed mechanism as follow, you have 3 steps. Okay, and the first step is, yeah, unfortunately, it's a fast step. Okay, so then we should be it's a sad face, right? Okay, so it's sad. Okay, and but it's not impossible. We could totally deal with it. Okay, and the second step is the slow step. So that's good. So we know that's our rate determining step. Okay, and then you go, what about the last step? It's also a fast step. We don't mind. Okay, because again, the slow step is what determines the rate. Okay, so then let's start from that point because that's what we really what really determines the rate. Okay, so the rate for the slow step, okay, will equals to K, okay, K times concentration of H2 times concentration of N2O2. Okay, you go, why can't we just stop here and use this to as the rate law of our overall reaction? If you look at the overall reaction, we have H2, that's fine, but look at this N2O2. Is it even inside? Is it even inside the overall reaction? No, it's not. Okay, so therefore, we don't think we could do that, right? We don't think we can use a substance which is not even in the overall reaction. So that means we need to replace this. Okay, so we need to replace this N2O2 with the substance from overall reaction. Okay, so now let's see how we can do that. Okay, so now let's see N2O2 actually also appears in the first step. Okay, and then from the first step is a fast step, and then we also recognize that's the equilibrium reaction. And after today, we all also mean what it means to us, right? For equilibrium, okay, so when you see the double-headed arrow, we know the rate of the forward reaction will equals to the rate of the reverse direction. Okay, so therefore let's start to work on this. Okay, so the rate of the forward reaction, okay, will equals to what? K1, okay, times NO squared. You go, how did you do that? Let's actually, let me write out this forward reaction for you. Okay, so what's this forward reaction? It will be 2 and 2. I'm looking at the first step, right? Okay, and then you goes forward. Okay, then you have N2O2. Okay, so in order to write down the rate law, then you recognize, right? So I have this, I have, oops, then have this, now I squared it. Okay, so that's how it happened. Okay, and now let's see what's the reverse. Okay, so the reverse direction, let's still look at the, so you have N2O2, right? Reverse, that means goes backwards. Okay, so I'll give it -1. Okay, and then you have 2 and O. Okay, so in order to write this down, I'm gonna borrow this one more time. Okay, so then the reversed will equals to K minus 1 and 2 O2 because it's going that way, right? Going from right to left. Okay, so now you have this 2. And then as we said, the key point was what? The forward reaction rate will equals to the reverse reaction rate. So now we can have a equal relationship. Okay, so then we're gonna have this one, right? The green equals to green, right? So equals to this. Okay, so they're equal to each other. Okay, then you go, I'm kind of got carried away. What are we doing here? Remember, we're trying to replace N2O2. Okay, now let's see. Ew, that's nice. We have an N2O2. Let's express N2O2 with everything else. Okay, so therefore I'll just pull N2O2 on one side, everything else on the other side. Okay, now I can use this, right? I can use this bunch over here. Let's use a different color. Pink. Okay, we can use this bunch, right? To plug back into this expression. Okay, so now let me put it down so then you see what we're doing here. Okay, so that's what we have. Okay, so we're gonna plug it in. Okay, so now I'm actually gonna do that. Okay, so now we can plug it in. So the rate will actually equals to K, that's a constant, times concentration of H2. Now this bunch will go inside here. Okay, so then you have K1 over K minus 1 times NO squared. Okay, and then as we talk about in the class, right? So that's a constant, but when you have numbers, constants are just numbers, right? So you can actually just combine them together. Okay, so after I combine them, I'm just gonna use a K. Okay, so that K again just represents a constant. Okay, you combine all this, you have this as the final answer. Let's take a look. I'm gonna bring this back to right next to our equation. See if this will make sense or not, right? Okay, so let's look over here. Okay, so look at our overall reaction. Okay, overall reaction, you have H2. Okay, you have N2. Sounds about right. Okay, so again, the actual observed rate Read law. Okay, you go. What do you mean observe? You did experiments, and then you find out the reaction order with respect of each reactant. It did come out as the way we just calculated based on the mechanism. Okay, and then that's how you do this type of question. Okay, so hopefully this is helpful. Thank you for listening.